Hello, honors students, and welcome to chemistry. And our first concept for Unit 1 is going to be all about measurements because chemistry is a quantitative science, which means there's going to be a lot of numbers. And we're going to be doing lots of labs, and we're going to be using lots of measurements in those labs. So we need to make sure that we do that 3 ways. We make them accurately, precisely, and in a way that makes sense. And that's what we're going to be talking about in these notes today. And hopefully a good bit of this is review for you. So first, a little overview. Like I said, chemistry is a science. Science is all about designing experiments and investigating things. And so that's what we're going to be doing in this class. And there's kind of a process that we generally follow in order to do that. And it starts with making observations. So you will be expected in this class to make both observations and inferences. And you need to know the difference. An observation is objective and it's based on your senses, whereas an inference is subjective and it's based on your perceptions. So for example, if you walked outside right now and looked at the ground, you could maybe see that there is a liquid on the ground. You could touch it and it could feel wet. These are objective things that you can do with your eyes, with your hands, that you can touch, that you can sense. And then you can make an inference. You can look at it and say, I wonder if someone spilled their drink. Or I bet it rained while we were in class. Or they were watering the grass over there and the runoff came into the road here. Those are inferences you can make that are subjective and based on what you're going to perceive in the situation. And oftentimes when we're doing this, it's going to lead us to ask questions, which is the next part in the process. But before we get there, I want you to pause and practice. I love this picture. Jot down some observations and inferences on your paper now, and we'll talk about those later. Okay, but let's keep going for the sake of the video. So again, you're going to make observations that will lead you to, come up with some inferences, and then that may cause you to ask some questions. You want to know some answers. Did it rain while we were in class? Well, let's figure it out. And so once you have a question, you're often then going to come up with a hypothesis, which is a testable prediction, typically of a cause and an effect relationship between variables. And you're going to design some sort of experiment to test out that prediction, to test out that hypothesis. You'll have an independent variable and a dependent variable, control group and experimental groups. You'll need lots of constants. And these are things we're going to practice over and over again every time we do a lab. And so in this course, because this is an honors course, we're not going to explicitly sit down and take notes on IV/DV again. Hopefully that excites you because hopefully it sounds boring to you because you've done it so many times, but we will be practicing this a lot. It's a critical part of this course. So we will be practicing that. And if you need extra review, let me know. I've got extra resources for you. But we're going to be doing lots of labs where we test these hypotheses, and it leads us then, once we design this experiment, to need to collect some data. And data can be either qualitative or quantitative, and both are good. We would like to collect as much data as possible to help see if our hypotheses are supported or not. So data, if it's qualitative, is based on qualities. And if it's quantitative, it's based on quantities or numbers and measurements. So for example, if I have an unknown substance in front of me, I could smell it, I could taste it, I could record the color of it. These are all qualities of it. It smells sour, it tastes sweet, it's the color red. That's all qualitative data. Those are observations I'm gathering that are based on qualities. But then I could also make quantitative measurements here. I could calculate the volume of it. I could, see what the mass is. Those are different measurements that we can gather. And that's why we're starting this unit in this concept talking about measurements, because we're going to be collecting a lot of quantitative data in this class. We're going to be using lots of numbers and lots of measurements. And so we need to be really, really comfortable with that. And then once you collect your results, oftentimes we're going to present those results graphically so that we have a visual summary of the data that we got. So we'll be making pie charts and bar graphs and line graphs and all sorts of things in here. And then we're going to analyze that data. We're going to say, what does the data show us? And we'll draw conclusions from it. We'll refer back to our hypothesis. We'll say if the data supports it or not. And then oftentimes it leads us to ask more questions and make more observations. And this kind of cycle and process happens all over again. And we're going to be doing this all year long. But I give you this context because, again, we're going to be zooming in right now in this concept about that quantitative data. And I want to show you the whole of it so you can see why this is important and why understanding and being able to make measurements and make them accurately and precisely is really, really important. Okay, so in class, we're going to pause and practice with this, but for the sake of this video, if you want to just jot down some examples of qualitative data with the pencil you're using to write your notes right now, and then some quantitative data, list those out and practice gathering as much data as you can about an object like your pencil, and we'll go over that in class. Okay, but let's keep going for the sake of the video so this isn't a million hours long. So like I said, we want measurements that we make to be accurate, precise, and make sense. So we need to know what this means. Okay, so first, accuracy. This is the degree to which the experimental result agrees with the accepted value. Okay, simplest way to put it, it's just how correct the measurement is. How close is it to the truth? Obviously, we want our measurements to be right. We want them to be the correct measurement. I'm 5 feet 5 inches. So if you come and you measure my height and you tell me I'm 5'8", that's not an accurate measurement because it's not close to the truth. I must be wearing heels or some other thing that's, messed up the accuracy of the measurement. Okay, so we really want our measurements to be accurate. We also want our measurements to be precise. Precision is the degree to which measurements agree with one another. Okay, so how specific the measurement is or how consistent multiple measurements are to each other is what we're looking at here. Okay, so you don't want to just say, oh, she's about 5 feet tall. That's not very precise. I'm 5 feet 5 inches. We also want our measurements to be consistent. We want them to be repeatable. So if 10 of you measured my height, if those measurements are precise, you're going to get consistent measurements over and over. Like you're going to keep getting around 5'5" for me, and you're all going to get that. When you're using a measurement instrument in lab, we're always going to estimate 1-digit past the amount you can read on the instrument. So if you're using a graduated cylinder and the lines on it are by milliliter, so you can see that the water level is at 20 milliliters, we want you to then estimate one more digit. So is it directly on the 20? Then put 20.0. If it's between 20 and 21, you're going to put like 20.5. If it's a little bit closer to 21, maybe you'll put 20.8 milliliters as your measurement, but we're always going to estimate one more over. And this is important. It's important that measurements are accurate and precise. Consider a sniper. Okay, a sniper is a very, very, very important shooter in the military that is expected to make very accurate and very precise shots. They'll be hiding in a building before they make some sort of shot, and they need to be correct, and they also need to be consistent. We need to trust that they can make the same shot over and over and over again so that their skills are consistent and trustworthy. Okay, so that's the difference between accuracy and precision. Here's a visual that may help. Okay, consider a bullseye if you're throwing darts. The target, the center, is the correct place to hit. That would be the accurate spot to hit. So this first dart thrower throws 4 dots, and I would say that they are precise and accurate. They are consistently hitting the target, and they're accurate because they're hitting the right spot. Now, this person is easy to teach. It's easy to coach this kind of dart thrower because, look, they're very precise. They're consistently making the same mistake over and over, but they're just not right. So you just got to figure out, how can I teach this person just to shift it a little bit so they can get to hit the target. Now, this dart thrower is accurate. Like, they're pretty much getting near the target every time, but they're not precise. They're kind of all over the place. So this kind of seems like they just had good luck. This would be a harder person to teach. And then this person is not accurate or precise. They're really not knowing what they're doing here. Okay, so hopefully that visual is helpful for you. So when we make measurements, though, we're not always going to be perfectly accurate or perfectly precise. We're humans. We're going to make errors. We're not going to be perfect. And that's where percentage error comes in. You need to be able to calculate a percentage error. This shows how far off a measurement is that is made in lab from the commonly accepted value. Okay, so here's how we calculate that. It's the absolute value of the experimental minus the accepted divided by the accepted, and then we'll times it by 100. Okay, so absolute value just means like this number can't be negative. We're not going to let it be negative. You're either 10% off. You're not negative 10% off. Okay, so let's do an example. Let's say you calculate the density of a substance in lab to be 2.10 grams per milliliter. The substance's correct density, like its known density, is 2.17 grams per milliliter. What is the percentage error? Okay, so what do we know? We know that our experimental, what we got in lab was 2.10, but the accepted is 2.17. And we're trying to figure out the percentage error. Okay, so I always like to put all the things I know and what I'm looking for on one side, and then I draw a line to keep my notes clear. And then now I'm going to plug it into the equation. Okay, so the experimental is 2.1, the accepted is 2.17, so I'm putting that down here too. All right, and when I calculate this, I get 3.23%. So my measurement was 3.23% off. This is going to be really valuable and something we're going to be doing in lab consistently. So it's a skill I want you to be comfortable with. We're also going to be calculating averages, because one way that we can kind of combat errors and inconsistencies in our labs is to make measurements over and over again. So to do lots of trials or to have a large sample size. But then when you're looking at data, it's not really helpful to look at 50 different measurements of the same thing. That's just a lot of numbers. So calculating an average helps us, because then it takes all of those numbers and it gives us one number to look at that represents all of the numbers. So an average is just the sum of the values divided by the number of values. So here's an example. Callie measures her flower to be 31 centimeters tall. Jay measures the plant to be 45 centimeters tall. Liam measures the plant to be 35 centimeters tall. Find the average of their measurements of the plant's height. So first, we're just going to find the sum of those values, 31 plus 45 plus 35, and then we'll divide by the number of values, which there are 3 measurements, so there are 3 values, so we will divide by 3. So we add those up first, we get 111 centimeters divided by 3. When you input that into your calculator, you get 37 centimeters. And that is an example of how you will calculate an average. Let's keep trucking. Standard units. So a standard is an exact quantity that people use for comparison. And the SI system is a standard system used by scientists around the world to make measurements. So basically, we want to be measuring things the same way and in the same language, so to speak, so that scientists in all sorts of different countries can share data with each other and compare their measurements. And so the SI system, each type of measurement has some sort of base unit, and then we use prefixes to make numbers bigger or smaller, not seem as overwhelming. And so that's what we're going to be looking at over these next few slides. So let's talk about standard units. So a couple of the things we'll be measuring. One would be length, which is the distance between 2 points. And this SI unit for length is the meter, which is abbreviated as an M. You'll use a meter stick or a ruler often to measure this. We'll be doing lots of length measurements. Also mass, just determining the amount of matter in an object. And the unit for this in the SI system is kilogram. So kg, it's that prefix there of kg. And we'll use a digital scale and a spring scale sometimes in order to measure the mass of some objects. Now, time is the interval between 2 events. And the SI unit for this is seconds, which is abbreviated as an S. And we'll measure this with a stopwatch often, or even just like on your phone, but lots of time measurements. Now, here's a new one that you may not be as familiar with, and it's the amount of substance. And this SI unit is the mole, which is abbreviated just MOL, mole. And this is used for measuring large amounts of really tiny things. So chemistry is all about atoms, and we're going to be and really it's all about electrons, and we're going to be talking about atoms and electrons in future concepts. But atoms and electrons are really, 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 really tiny, and so matter has lots of atoms in them. And so we're going to be using really tiny numbers and really big numbers. And so one of the ways that we make those numbers more manageable is by using the mole to represent how much there is. So if you have 1 mole of something, you have this much of it. Okay, that's a lot, right? I told you a lot of a tiny thing. And scientific notation, which we'll talk about in concept 2, that's 6.02 times 10 to the 23rd. Okay, so that's what a mole is. Now, this is a mole as an animal, and this picture is cute, but this is not the kind of mole we're talking about. And I don't want you to be overwhelmed by this. Y'all are going to be so familiar with the mole. It's going to be your best friend this year. We'll talk about it more, but I just want to introduce this now because this is an SI unit that we'll be using a lot. That's newer for you. You've probably taken time measurement and mass measurements, but maybe not amount of substance measurement. So we'll be using the mole for that. Last one I want to introduce with you here is temperature. And temperature is a simplified definition is it's the amount of heat in an object. And we'll have a more precise definition later on in the year. But for now, just consider it the amount of heat in an object. And the SI unit for temperature is Kelvin, which is a big K. Now, the metric system uses Celsius, and the United States, we use Fahrenheit. But in science, we're going to use the Kelvin. So we need to be able to convert measurements into Kelvin. And we're going to do that with temperature conversion. So these equations are going to be really helpful. So if you know the degree Celsius, you can just add 273.15 and you'll get Kelvin. And now you may be wondering, like, why? Why this big number? The purpose of Kelvin is really to get out of negatives because you can't really have a negative amount of heat. And so that's where Kelvin comes in with these bigger numbers. But again, we're going to just be able to use them interchangeably because we'll use these equations. If we know Fahrenheit, we can find Celsius. If we know Celsius, we can find Fahrenheit. And so these are equations we're going to get familiar with using. Now, I know you may be a little bit intimidated by doing calculations, and I don't want you to be. Chemistry is all about problem solving, and problem solving skills and critical thinking skills are going to carry you through the rest of your life. And so I want to give you strategies to do that, even if, math isn't like your favorite thing in the world. Okay, so I'm going to teach you a strategy called R.A.D.A.R. And this is where we're going to stop for standard units. There's also 2 more SI units. There's the ampere for electric current and then candela for luminous intensity. But since we're not going to really be using those units in this class, we're not going to write anything down for those. But I just wanted you to know that there's those units as well. Okay, so let's talk R.A.D.A.R. This is a strategy I want you to utilize whenever you get to a problem and you feel lost. Okay, so the R stands for read. First thing you're always going to do is read the problem and figure out, what am I looking for? What's this even asking me? And then you're going to analyze, what is the information they gave you? Let's label what we know and what we don't know. And then we'll diagnose. You're going to have a reference sheet in my class with equations for each unit that you can reference. So use that reference sheet, use the information provided to you, and diagnose, like, what's the plan? What can we do with this information to move forward? Then you're actually going to assess and you're going to carry out that plan and solve the equation. And then we're going to reflect, and this is so important. We're going to look back and say, does the number make sense? Like I said, measurements need to be accurate, they need to be precise, and they need to make sense. And oftentimes, I see it all the time. A student will get like a crazy weird number, and they did all of the work right. They just put it in their calculator wrong. And if they had just stopped for a second and reflected and thought about this number that they got, and they may have realized, like, oh, that's kind of a crazy number. That's probably not right. I may have punched something in wrong. I may have put too many zeros, got a little trigger happy with the calculator. Okay, so reflecting is really, really important. So let's put this into practice now. Let's say I give you this problem. Mrs. Benton is pregnant. Her body is super sore and she would like to take a bath. Her doctor told her this was fine as long as the bath wasn't more than 98 degrees Fahrenheit. She finds a thermometer in the junk drawer and places it in her bath water. It reads 38.5 degrees Celsius. So is she safe to take a bath in this water? All right, let's do R.A.D.A.R. We just read the problem. Now let's analyze. What do we know? We know that the water is 38.5 degrees Celsius. Okay, what do we want to know? We want to know what that means in Fahrenheit so that we can know if it's hotter than 98 or not. Okay, so that we just analyze. Now let's diagnose. Go back to these equations. Which will be the most helpful? If we know Celsius and we want to find Fahrenheit, you always want what you're trying to find to be isolated by itself. So this last equation is going to be the most helpful because we can plug in Celsius and get Fahrenheit. Okay, so let's do that. We're going to use this equation. Okay, so we just did the diagnose. Now we're going to assess. So I like to draw a line so that all of my planning is on one side and then all my problem solving is on the other. So now let's plug it in. Let's assess it. So instead of C, we're going to put 38.5. And then when you're actually solving, remember, order of operations. You do your parentheses first. So 38.5 times 9 divided by 5 gives me 69.3. And then I'm going to add 32. And I get 101.3. So now reflect. You don't just stop here. What was the original question? The question was, is she safe to take a bath in this water? The water is 101.3 degrees Fahrenheit. Is she safe? No, because the doctor said it can't be more than 98 degrees Fahrenheit. Okay? Now, this is where, like, let's say you did this and you got a number like 1,000. That's where when you reflect, you're like, does it make sense that I got a temperature and that's 1,000? That seems like a giant temperature. And that's where you may realize, like, oh no, I just made a calculation error. And so that's where the reflection, again, is really important. And so we're going to be using this R.A.D.A.R. strategy all the time, all year long. I'm going to always show my work this way when I'm doing examples for you so that it's hopefully clear and organized for you to follow along with. Okay, So, like I said, we want our measurements to be accurate and precise, but we also want them to make sense. We want to use units that make the most sense. So, for example, how many seconds are in 1 minute? 60. How many minutes are in 1 hour? 60 minutes in 1 hour. Okay, so let's say we know these are things that we know. Let's say I wanted to tell you how long it takes me to drive home from school. And if the answer is 15 minutes. But would it make sense for me to tell you how many seconds it takes me to drive home or how many hours it takes me to drive home? What would make the most sense? Okay, well, let's think about it. If there's 60 seconds in 1 minute, that means that 15 minutes, which is how long it takes me to drive home, is the same as 900 seconds. And if there's 60 minutes in 1 hour, 15 minutes is the same as 0.25 hours. Okay, now I could tell you it takes me 900 seconds to drive home, or I could say it takes me 0.25 hours to drive home. But if I told you either of those measurements, it wouldn't really make sense to you. It makes much more sense if I just tell you 15 minutes. Even though all three of these equal the same thing, I want to use the measurement and use the unit that makes the most sense. And so that's where we're going to be using something called conversion factors. Conversion factors help us make our measurements make the most sense by putting them in the unit that makes the most sense. Okay, so a conversion factor is just a ratio of equivalent values, meaning they equal 1. So when you need a measurement in different units, but you obviously don't want to change the value of the measurement. Like you don't want to change the actual number, what it's worth, because you need it to be accurate, but you want it to be in a unit that makes more sense. And this happens all the time in the real world. Y'all will be amazed how much you're going to use this skill. So when you're baking and cooking, like I have a recipe for pancakes and it makes 10 pancakes. But if I have some friends over, I'm going to need to make like 30 pancakes. I'm going to have to take all of the ingredients and times them by 3 and convert them into 3 times the value so that I know how much I need to make. Okay? Traveling to different countries, like using different foreign currencies. If you see a souvenir in a country you're traveling to and you want to know if you can afford it, you're going to need to do some math there to figure out what it is in dollars or whatever currency it is that you use. Okay, purchasing products from different countries. A great practical example of this is the formula shortage that happened in the United States in 2022. So in the United States, most baby bottles have measurements on them in ounces because formula in the United States comes in ounce measurements. So they'll say, hey, you need 8 fluid ounces of water with 4 scoops of formula. Well, during the formula shortage, the US had to import a ton of formula from Europe and Australia in order to, meet supply and demand because so many people needed formula and it wasn't available in the United States. Well, a lot of these European formulas, the measurements were in milliliters. And so moms were having to do these conversions from ounces to milliliters to figure out how much to feed their baby in the bottles that they have. So this is a really real world example. Building and engineering this is useful for. My brother is a civil engineer and he has told me how when they process design, it's all done in metric, but then the people working in mechanical design, like in piping and HVAC, they use the imperial system. And so they're all constantly having to convert each other's measurements to make sure that they're on the same page and their things are working together correctly. Okay, so we need conversion factors. They're so useful. So here's an example of a conversion factor. There are 24 hours in one day. Okay, so these 3 dots mean therefore. So because of this, therefore, 24 hours equals 1 day. 1 day equals 24 hours. This right here, that's a conversion factor. Okay? If I told you it took me 24 hours to do something or it took me 1 day to do it, I would be saying the exact same thing because that's a value that's equal to 1. Okay, so we're going to be using these a lot. We're also going to use prefixes. Like I said, we don't want to use really giant or really tiny numbers. So prefixes help us to attach to a unit just to make the number make a bit more sense. So for example, milligram, milli is a prefix attached to gram, and it's represented by mg. So we have all of these different conversion factors that we can use, okay? So don't let this overwhelm you. So a base unit is just depending on what you're measuring. If you're measuring length, that's meter. Mass, it's grams. Volume, it's liter. Time, it's seconds, okay? And all this tells me is what the prefix means. So 1 kilo of something is just 1,000 of it. So 1 kilometer is the same as 1,000 meters. Or 1 kilogram is the same as 1,000 kilograms. Down here, 100 centimeters is the same as 1 meter. Or 1,000 milliseconds is the same as 1 second. Okay, so that's where we're going to be using these prefixes. And these values are going to be given to you in my class. So 1 kilogram, same as 1,000 grams. 100 centimeters, same as 1 meter. And we're going to use these to convert measurements so that they make the most sense. Okay, so here's how we do it. There's a process we can walk through every single time. You write down the given number and unit, and then you're going to draw a picket fence, something like this. And then you're going to use a chart that I'm going to give you on a reference sheet of conversion factors and figure out which ones you need. And you're going to put those on opposite ends. You want the units to be opposite so that they'll cancel out, because we're basically doing a big multiplication problem here. Then you'll multiply across the top and bottom, and then you'll divide, and that's how you're going to get your answer. Okay, this is a lot easier seen in practice. So let's put it to practice. Okay, let's do an example. Let's say I want to know how many meters are in 51 kilometers. Okay, so what do we know? Let's do R.A.D.A.R. We know kilometers is 51. What do we want to know? We want to know meters. Okay, let's diagnose. Look at a reference sheet. If you're in my class, you've been given a reference sheet of conversion factors, or go back a couple slides and see those. What do we know about meters, which is a base unit, and kilometers, which is a prefix? Well, we know that there's 1,000 meters in 1 kilometer, so we can use this. Okay, so now we're going to assess. We're going to actually solve. Okay, so follow the steps. Write the given number and unit, 51 kilometers. Step 2, draw a picket fence. Step 3, okay, we're going to put in the conversion factor. So 1 kilometer is the same as 1,000 meters. But how do I know which goes on the top or the bottom? You want the units to be opposite of each other. So I'm going to put a kilometer on the bottom is the same as 1,000 meters. And the reason I do that is so that then those cancel out. And all I'm left with is meters, which is what I'm looking for. Now I multiply across the top. 51 times 1,000 is 51,000 meters. And then across the bottom is just 1. And then I'll divide, and I get 51,000 meters are in 51 kilometers. Okay, let's try it again. Use R.A.D.A.R. How many kilograms are there in 12,135 milligrams? Okay, so we just read. Now let's analyze. What do we know? Well, milligrams is 12,135. We want to know kilograms. All right, let's diagnose. Look at your reference sheet. What kind of values can help us get there? Well, there's nothing that goes directly from milli to kilo, but we know that there's 1,000 milligrams in 1 gram. And we also know that there's 1,000 grams in 1 kilogram. So we can use these. So write the given number and unit. Okay, so 12,135 milligrams. Step 2, draw a picket fence. Step 3, let's fill in these conversion factors. And we're going to put the matching units opposite so they cancel out. So first, let's start with milligrams. So I'll put 1,000 milligrams in the bottom. That's the same as 1 gram. This is a conversion factor. And then, so that'll let the milligrams cancel out. Now I got to get rid of these grams. Well, there's 1,000 grams in 1 kilogram. So I'm going to put those opposites so they'll cancel out. So those cancel and those cancel. Now we just multiply across. 12,135 times 1 times 1 is 12,135 kilograms. That's my unit that's left. And then 1,000 times 1,000 is 1 million. Now I divide, and I get 0.012135 kilograms is how many kilograms are in 12,135 milligrams. All right, so I want you to pause, and I want you to practice and do these 3 practice problems, and we'll go over these in class, okay? And then we're also going to do some more practice with measurements. But again, for the sake of the video, I'm going to keep trucking on, and we're going to talk about our last thing, and that's significant figures. So again, remember, the best measurements are accurate, precise, and they make sense. And that's where sig figs come in. Okay, significant figures, significant digits, sig figs. These are just the number of digits in a measurement that reflect how accurate the measurement is. They help us. This is where they really help us. They help us know how much to round our answers when we're doing calculations, because we want to make sure that the answer that we are reporting, it's not more precise and more specific than the measurements that we started out with. Okay, that's where sig figs comes in. So for example, density is mass divided by volume. D equals M over V. We're going to use this so much this year. So find the density of a penny. Okay, so if you want to do that, let's see what would we be looking for? Well, we're looking for D equals question mark. And in order to do that, we're going to need the mass and the volume. Okay, so therefore we'll need to measure those. So we would take a penny, we would go get the mass, and then we'd go get the volume, and we divide. Now, when you're getting the mass, you're using a scale. It's probably only going to be like 2 decimal places specific. So let's say you get the mass and it's like 2.50 grams. And then let's use water displacement. We figure out the volume is like 0.35 milliliters. When you divide 2.5 grams by 0.35 milliliters, you get 7.142857143 grams per milliliter. Okay, that's a really crazy specific number. That's a number that like a NASA astronaut can get. we're just normal people. Okay, so we're not going to be able to get numbers that specific. So we need to know how many sig figs there are, because that's going to tell us how specifically we need to report our answer. Okay, and there are rules to figure this out. Now, I can only speak for my students. If you are in my class, I am not going to make you memorize these rules. I'm going to give you these on the reference sheet, but you need to be able to use them and apply them. Okay, that's really important. So let's talk through them. I can't speak for other people, students of other teachers watching this, but hopefully it's the same. You're not going to have to memorize these. All right, so here, we got to know what is not significant and what is. Okay, what is not significant? Placeholder zeros. Okay, so zeros that are just there to hold a place. It'll make sense in a second. Okay, what is significant? Non-zero numbers always count. Okay, so here's what I mean. 411 has 3 sig figs. 411. That's 3 non-zero numbers. They all matter. Okay, they always matter. Sandwich zeros, meaning they're between non-zero numbers, always count. Okay, so let's look at this. 404. The 0 right here is significant because it's sandwiched. So this is 3 sig figs. That 4, that 0, that 4, they're all significant. 3 sig figs. But a number like 440, this 0 is not significant because it's just a placeholder. That's only there to make sure I know it's 440 and not 44. And so this only has 2 sig figs. The other thing that is significant is trailing zeros. So zeros like this, but only if a decimal is present. So this is a trailing 0, but there's no decimal, so it's not significant. But let's look at these. Okay, this 0, not significant because it's just a placeholder. These zeros are significant because of the decimal. So 1, 2, 3, 3 sig figs. These 3 zeros are all placeholders, so they're not significant. The only sig fig here is the 5. And then right here, 5,000. The only sig fig here is the 5. Okay, because these are all just placeholders and there's no decimal. So that's just 1 sig fig too. Okay, this seems a little overwhelming when you first look at it, but we're just going to be practicing this over and over again. And so I don't want it to stress you out, okay? So I want you to pause here and I want you to practice these, okay, so that you can figure out if you're going to be getting good at this. And then we'll practice more in class too. But the last thing I want to tell you about before we do that is I want to give you rules for calculations, because this is really where this is going to come up for you practically in this class. When you're adding and subtracting and multiplying and dividing, and then you need to round your answer. Okay, so when you're adding and subtracting values, look at sig figs only to the right of the decimal. So if there's like 2 sig figs to the right of the decimal, then you're going to round to the 2 decimal places. If there's 1 sig fig, you'll round to 1. Okay? When you're multiplying and dividing, you're going to look at all the sig figs. They all matter, not just the ones after the decimal. In both, your final answer should never have more sig figs than the least number of sig figs in any starting value. Okay, let's do an example. All right, let's say I want you to calculate 110.4 milliliters minus 8.75 milliliters. Okay, so this is adding and subtracting. So when you're getting your answer, you're only going to look at the sig figs to the right of the decimal. So don't even worry about these first ones. So to the right of the decimal right here, there's 1 sig fig, and right here, there's 2 sig figs. So in terms of rounding though, your final answer should not have more sig figs than the least number. So we're going to round to 1 because this number only had 1. And so we're going to round our answer to 101.7 milliliters. Okay, let's do another example. Division, 202 grams divided by 39 milliliters. Okay, so in multiplying and dividing, we're looking at all the sig figs. So right here, this number 202 has 3 sig figs because that's a sandwich 0, and this one has 2. But in your final answer should not have more sig figs. So we're going to default to 2 because that's the least number of sig figs we have here. And so our final answer, we will round to 5.2 grams per milliliter, which is 2 sig figs. Okay, I promise this will get easier with practice, and that's what we are going to do right now in class. So do not fret. We will practice sig figs. And I hope this introduction to measurements, which we'll be doing so much in chemistry, is helpful for you starting this year.